Hello AP Stat. Today we're going to start by looking at the conditions that need to be met to analyze data with linear regression. The regression line, that is the least squares regression line that we talked about in our last lesson, is not meaningful unless data meet three conditions. First, all variables are quantitative, not categorical. If you think about it for about 5 seconds, I'm sure you can understand why a categorical variable would not be suitable for regression analysis. Try fitting a line of best fit through categories. It gets ugly. The data suggest a linear relationship. All right, we don't want data that look curved in nature or chaotic in nature. We need to observe a linear relationship, either going up and to the right or down and to the right. And finally, there are no outliers, since there can be no data points that could skew an otherwise strong correlation to look weak, or believe it or not, vice versa. With large data sets, this is not as much of an issue, as we'll see later in the chapter. Now, there are three conditions right here. Quantitative data, that should be obvious. Linear relationship, also obvious. No outliers, not quite as obvious, but outliers do tend to ruin things now, don't they? There is another condition, but we need to talk more about residuals before we introduce that one. So stay tuned. There are actually 4, but we're going to keep 3 in our back pocket. Now we're going to talk about the regression line in real units. The regression line in real units, by the way, that's opposed to standard deviations, which are the units of standardized data, which we talked about in the last section when we were talking about how we got the correlation coefficient R. Regression line in real units can be given using this equation. This is y hat, our predicted y values, given particular x value inputs. So these are two variables, x and y, that are related in our scatter plot. We input x values into the regression line to get predicted y values. And then we have these two characters right here, b sub 0 and b sub 1. If you are using a different textbook, these may be a and b respectively, and we'll talk about that. There are different representations. This is my personal favorite. College Board has a different representation. It's equally good, but this is my personal favorite, and I'll let you know why in just a little bit. Note that this line is in the classic y equals mx plus b form. Well, it's really y equals b plus mx, but whatever, but with different variables. Given the means and standard deviations of the two variables, as well as the correlation coefficient R, we can also say that B1 is equal to R, correlation coefficient, times the standard deviation of our Y variable divided by the standard deviation of our X variable. And then we take this B1 after evaluating, and then we substitute it into here to find B sub 0. And those are the ingredients we need to form our regression line with real units. That is, the units of the variables we're actually given, our actual X variable units, our actual Y variable units, as opposed to just the standard deviation of X and the standard deviation of Y. Note that the units of b sub 0 are the units of y. All right? This should make sense. If we have any situation that we can model with a linear equation, the y-intercept is going to have the same units as the y variable. And the units of b1 are the units of y divided by the units of x. B1 is a coefficient of x. It's a slope. Slope is rise over run, hence the y divided by x. All right, this is just a breakdown of how the College Board's AP Statistics formula sheet presents these formulas right next to your textbook's representation. As I say in the description, I'm teaching out of Stats Modeling the World by Bock, among others. I like their representation of this formula, namely because b sub 0 and b sub 1 are related to two variables called beta sub naught and beta sub 1 that we will talk about later on in the year. Okay, so I like that correspondence between the B's and the betas, all right? But this is no less an expression of the same formula. You got your predicted Y values and you got your X inputs right here. Just know that B naught is the same as A and B sub 1 is the same as B no subscript, and you're good. So now we're going to find the regression line given some sample statistics, all right? So we're going to use the equations for B sub naught and B sub 1 to find the regression equation, okay? And that regression equation is going to be our Y variable is speed and our X variable is height. We are inputting heights to predict speeds. So we're going to input our B sub 0, our B sub naught right here, and our B sub 1 right here. And then we're going to state the units for B sub 0 and B sub 1. Here is our equation for B sub 1. Here's our equation for B sub 0. You need to find B sub 1 before you find B sub 0. One must wonder why we didn't order the subscripts in the order that you would need to find them. That is for the big dogs of statistics, not for me. I'm just the messenger. So give this one a go. Feel free to pause the video. And don't forget about R. You're going to need R for B1. Give it a go, pause the video, check your answer once you're done. Okay, I'll assume we're ready to continue. Here we go. So B1 is going to be our correlation coefficient, 0.81 times 8.6. That's my standard deviation of the Y variable speed, divided by 18.8. That is the standard deviation of the X variable, and we get this fun little decimally number that is an approximation, of course. Now let's look at B sub naught. We have 37.7, that's my mean Y value, minus my value for B1, the 0.3705, times 59.3, the mean X value, and I get this value for B sub 0. All right, again, fun decimally guy. It's an approximation gleaned from an approximation. This is a good principle for statistics. 4 places to the right of the decimal point is often A-OK. Best to use more accurately rounded numbers in the calculator, but this will do for right here. Now we need to input them into the regression equation, and so we will do just that. Now let's talk about the units for B1 and B0. My units for B0, my B naught, are going to be the same as my Y variable. So it's going to be miles per hour. So this 15 number, that is a certain number of miles per hour. Now, my B1 value is a little more complicated. Remember, it's a slope. A slope is a ratio. It's going to be my Y variable divided by my X variable. So this is going to sound interesting and perhaps wrong, but these are the units. The units for my B1 are miles per hour per foot. All right? Y variable over X variable, miles per hour per foot. So now that we've found a regression line, we need to make sure we're understanding how to interpret this regression line properly. The regression line gives us the best estimates possible, considering the whole data set, but never a guarantee. Okay? We are estimating Y values. We're predicting Y values given X value inputs. We are never guaranteeing anything to happen. So we should not say, for example, for every 1 gallon, a car will travel 27 miles. If our input is 1 gallon and the regression line spits out you're going to go 27 miles, that should not be interpreted as an absolutely your car is going to go 27 miles because the regression line says it will, okay? Instead, we would say the model predicts that for every 1 gallon, the car will travel 27 miles, right? What we know for certain is that we're inputting 1 gallon into the regression equation, and then the model predicts the car will travel 27 miles. Now, this may not seem like a really big deal, but one, to say that regression lines tell absolutes is absolutely wrong, and the AP test is going to get you on this if you're not careful. So you need to use some language of humility, language that is not deterministic in nature. So we are not determining things using the regression line. We are predicting things with the regression line. So here we're going to apply the skill of interpreting a regression line. We're going to look again at the relationship between the price in US dollar and the house size in square feet in Saratoga, New York. And the regression model is the same as before. So first question, actually seventh question if you're counting, what is the slope and what are its units? This is number 7 because we did numbers 1 through 6 in the last section, if you're still curious. So what is the slope and what are its units? Take a moment, think about it, and unpause the video when you're done. All right, I'll assume we're ready to go on. The slope is going to be 88.67, and its units are dollars per square foot. So this is our B1 value, and it's a slope. And the units are going to be the units of y over the units of x. So it's going to be dollars per square foot. Okay? So now how do we interpret this slope? And we need to be careful with this one. We need to make sure we're not using deterministic language. Okay? And there are some magic words that we learned that keep us humble. The model predicts. Oh, these words are so important. If you don't include these words, you have a strong chance of using deterministic language, and that is going to cost you in a free response problem on the AP test. The model predicts that the price of the house increases by $88.67 per each additional square foot. All right, so we are increasing, the model predicts, this amount of dollars per each additional square foot of our house in Saratoga, New York. Is the model's intercept meaningful? This is a question I can almost guarantee you will see on the AP test somewhere. Is the model's intercept meaningful, and explain? Well, think about it. Pause the video. Is the intercept, first of all, what is the intercept? And second, is it meaningful? Okay? Think about it. Unpause the video when you have an answer. Okay, I'll assume we're ready to continue. Well, the y-intercept is this 8,400. All right, that's our b sub 0. Now, is that meaningful? All right, does that 8,400 number matter for any other reason than it's in the regression equation? And if we're inputting a size, we're going to need it in our calculation. Is it useful in its own right? And I'm going to argue it's not. And here's the reason. The model's intercept, 8,400, is not meaningful because it gives the price of a 0 square foot house. So that's not useful to us. If we're buying a house, I hope it's more than 0 square feet. 0 square feet does not a house make. I've seen cardboard boxes that are bigger than 0 square feet. I've seen thumbtacks that are bigger than 0 square feet. Anyway, your house is 1,000 square feet larger than your neighbor's. How much more is the estimated worth, that is price, based on this linear model? This one's a little more nuanced and tricky, although you might be able to get this. Feel free to pause the video and try this one on your own. Okay, I'll assume we're ready to continue. Here we go. The model predicts that your house is take the slope and multiply it by 1,000, and we get this 88,670 more than your neighbor's house. All we would need to do is ignore this fella that we just explained is meaningless in its own right. Poor buddy. You're useful for the regression equation, just not right now. This is the real hero right here for number 10, and for other examples as well. We would take this, multiply it by its size, and that's how much more expensive a house that's 1,000 square feet bigger would be than the other house. We predict, of course. Now here's a problem similar in style to something you'd see in the homework, and similar in style to perhaps a free response question. So let's give this one a go. We're going to consider the data for the age at inspection in years and condition on a safety rating scale of 1 to 7 of bridges in Tompkins County, New York. We're just spending a lot of time in upstate New York in the scatter plot below. So first, we're going to determine whether the data meet the conditions to compute the least squares regression line, which would be quantitative data. Yes, the data are quantitative. Very good. Moving on. Linear pattern. You got some outliers up here, but there does seem to be a down and to the right. And no outliers, not quite. There are only a few outliers, but there are like a bajillion data values over here. So 1 or 2 outliers, like I said before, is not going to destroy you. Now we can find the equation of the regression line by first finding B1 and B0. So take this information right here and the correlation coefficient and see if you can find B sub 0 and B sub 1. Pause the video, give it a go, check your answers when you're done. Okay, I'll assume we're ready to continue. Here they come. So B sub 1, here is our substitution for that. We have R, S sub X, and S sub Y and S sub X. So you have R, your standard deviation of your Y variable, and your standard deviation of your X variable, and it evaluates to about this right here. Then we substitute that in to find B sub 0. We would have Y bar right here, the mean Y value, the mean X value, and we have our value for B sub 1. That gives us B sub 0. That allows us to write the regression line. Our predicted condition on a scale from 1 to 7 is going to be 6.178 approximately minus 0.0196 times the age at inspection. So we input ages at inspection, and we can predict with, I guess, decent accuracy, the condition of the bridge. So now we're going to move on to number 3. We're going to interpret the significance of the regression line to answer the question. All right. So, is there a relationship? Well, R is not 0, so there's some kind of relationship. Is it an accidental relationship? Well, honestly, this is a little applied logic. The older the bridge, the worse condition it's going to be in generally. You have these bridges that may as well have been built by the Romans, and they're just going to kind of last forever. But most bridges go the way of, anything that people build. Things get older, and they degrade in quality. Okay? So there is a relationship. We should expect a relationship. The correlation, it's not insanely good. It's not in the 0.8s or the 0.9s, but it's there. There are some outliers, but this is real-world data, and that's really not bad for real-world data. So we're going to say there is a relationship, all things considered. There is, in fact, a weak, negative, linear relationship between age at inspection and condition, all right? Is it strong or weak? It's pretty weak. Is it positive or negative? Down and to the right, it's negative. And there is a linear relationship. Hence, we can compute a least squares regression line in the first place. Now let's look at letter B. What do B sub 0 and B sub 1 tell us? All right, what is the significance of those quantities? Well, B sub 0 says the model predicts a newly made bridge has a safety score of about 6.178. That's important to note because last time we said that B sub 0 really has no meaning in and of itself. That was in the problem about the costs of houses in Saratoga, New York. Here in Tompkins County, New York, our B sub 0 does mean something. You can have a bridge that was just built. Bridges are built every day, all right? There are quite a few bridges that have been built very recently. And the prediction for a newly made bridge is it has a safety score of about 6.178. Now let's talk about B1. B1 says the model predicts for each increase of 1 year, the safety score decreases by that number. Okay, so we're predicting a small decrease per year, and keyword predicts. We're not using deterministic language. We want to stay above that. So, part C. What are the limitations of the study? This is a common question in statistics. We can't just take information and apply it anywhere we would like to apply it. Okay, we need to look at where this study should be applied and apply it no further. So we're going to refer to the location of this study. This study was done in Tompkins County, New York. So we should only apply it to that area, okay? We may take this information and apply it to places around Tompkins County, perhaps in climates similar to Tompkins County. But if we were going to apply this information to, I don't know, bridges in Mexico City, the climate is very, very different in Mexico City, okay? So bridges are going to experience wear and tear differently depending on their climate, all right? Maybe bridges do better in Mexico City. Maybe bridges do not do better in Mexico City, all right? Maybe bridges are made better in Mexico City. Maybe they're not made as well. I don't know. But we should not think that we can apply this to all bridges everywhere. We should apply it to places that are similar to Tompkins County, New York, in terms of the climate and perhaps the quality of construction as well.